In this lecture, we will talk about the meaning of inertia, and then we'll talk about what mass is, how mass is related to inertia, and how mass and weight are different from each other. And we'll introduce force, and then we'll also talk about how we combine more than one forces when we apply multiple forces on an object. So objects have tendency to stay in its original state. If it is at rest, it tends to be at rest. If it is in motion, it tends to be in motion. So that's the inertia. And mass is measure of the inertia of the object, meaning more the mass, more is the inertia. Okay, and vice versa. More the inertia, more is the mass. If you have a bigger mass versus a smaller mass, so the bigger mass will tend to stay at rest. It will take more effort to bring it to motion. And if you have a bigger truck versus a smaller car, it will take more effort to stop the bigger truck compared to a smaller car, because the bigger truck has more inertia or more mass. Another term is the weight. Weight and mass are different things. Weight is basically how much gravitational pull there is on an object. Okay? Weight depends on mass. More the mass, more is the gravitational force. So twice the mass, twice is the weight. Okay? If you have 2 kilogram object versus 1 kilogram object, the 2 kilogram object will have double the weight compared to 1 kilogram. And the reason for that is weight is basically the multiplication of mass and this constant quantity. So weight is mass times g. That's why if you double the mass, you double the weight. If you triple the mass, you triple the weight. Okay? So they are related to each other. But again, the difference is mass is a constant quantity no matter where you go in the universe, whether it's on the moon or on the Mars or on the Earth, the value of mass is always same. Whereas the value of weight depends on the value of g, this g, and this g depends on planet to planet. For example, if you are talking about the surface of the moon, the value of g is only 1/6 that on the surface of the earth. If a person weighs 60 Newton on earth, then the person will weigh only 1/6 that of that weight on the moon. Okay, so on moon the person will weigh only 10 Newton. So weight is not same everywhere, it depends on planet to planet, whereas mass is same everywhere. Force is simply push or pull, and if there are more than one force applied on an object, so you have an object, you apply force of F1 to the right and force of F2 to the left, so you have more than one force. In that case, the net force on that object would be sum of these two forces. Okay? Sum doesn't mean you just need to add. Okay? It doesn't mean just adding. Sum could, in physics, sum could also mean subtraction. How is it subtraction or addition? It depends on the direction. If you are considering something going to the right, we consider the sign to be positive. If you consider something that is pointing to the left, we consider that sign to be negative. Okay? So whenever we say
sum of two forces, we consider this notation, this notion. So F1 is positive because it's pointing to the right, and then F2 would be negative because it's pointing to the left. Okay, so that will give us the net force, F net. Okay, for example, let's see the first picture here. On the first picture, we see there is 5 Newton force applied to the right and 5 Newton force applied to the also to the right, and the net force would be, so this is to the right, so this is positive, this is also positive, and when you add two positives, you get 10. Okay, 5 plus 5 is 10. On the second picture, you see one is applied to the right, so this is positive, the other one is applied to the left, so that's negative. So you are adding 5 to negative 5, and that gives us 0. So 5 minus 5 is 0. Likewise, on the third one, we have 10 and 5. So the one applied to the right is positive, this is negative. So 10 is positive, and this one is negative, so minus 5. That gives us 5. Okay, and if you get the answer to be positive, so you get 5 Newton, so that means you are getting positive answer. What that implies is the net force would be on the right side. Okay, let's say you have a force applied to the left, say 10 Newton, and you have 2 Newton force applied to the right. So we have 2 Newton is positive, this is to the right, and we have 10 Newton negative, so that's negative. So that gives us minus 8 Newton. Okay, 2 minus 10 is 8. So this negative sign implies that our net force would be to the left. Okay, that would be the net force. So again, this notion is very important in physics. Anything that points to the right, we consider that to be positive. Anything that points to the left, we consider that to be negative. And also, if something points to the upward direction, we consider that to be positive. If something points to the downward direction, we consider that to be negative. That's very common notation we use in physics. Okay. So based on the sum of the forces, we use, or we term this equilibrium rule. We state equilibrium rule, which states that if you apply bunch of forces on an object, okay, so you apply one force, say that's F1, another force, let's say F2, you apply another force on this side, let's say F3, you apply another force here, F4. Okay, if these forces all add up to 0, then this object is said to be in equilibrium. So when an object is in equilibrium, what that means is the force exerted on the object, they all add up to 0. Okay, what that means is our F1 is positive, it's pointing to the right, that plus F2 is also positive, pointing to the right, and then we have F3, which is pointing to the left, so that's minus F3, and we have F4, it's also pointing to the left, so that's minus F4. If the sum of all these forces is 0, then we know that this object is in equilibrium. Now this will be more clear when we talk about Newton's second law and acceleration, so we'll come back to this again later. We can have two types of equilibrium. One is called static equilibrium, other one is called dynamic equilibrium. So static equilibrium is you apply force on an object, okay, same force on the two sides of the object, and the object doesn't move. Okay, so the object remains at rest. So this kind of equilibrium is called static equilibrium. So in case of static equilibrium, the object remains at rest after applying a bunch of forces. So if I pull this object on the right and on the left, but the object doesn't move, then this is at static equilibrium. Okay, Another equilibrium is dynamic equilibrium. So let's say this object is already moving. Okay, it's already moving, and I apply some force on this side, apply force on the left side, and my force does not change the speed or the velocity of the object. Then it's in dynamic equilibrium. So the meaning of dynamic equilibrium is object is moving at some speed, let's say 2 meters per second in the beginning, and while it's moving I apply some force, let's say 5 Newton on this side and 5 Newton on this side. So this 5 Newton, why it's doing that? So this 5 Newton will cancel this 5 Newton, and this object will keep moving at the same speed. So the speed doesn't change. It's still moving at the same speed. So this is dynamic equilibrium. So whenever we say equilibrium, some people think that it means the object is not moving, but that's not true. Equilibrium doesn't mean the object is at rest. Depends on what kind of equilibrium we are dealing with. The object can be either at rest or moving. If it is at rest, it will remain at rest, okay, by applying the force. The force doesn't change the state of the object, it just stays at rest. So that's again static. In case of dynamic equilibrium, the speed of the object at which it's moving, it remains same. It keeps moving at the same speed. The force doesn't change the speed. So let's look at a problem, a multiple choice question. A bowling ball is in equilibrium. So when can we say that a bowling ball is at equilibrium? So you have a ball. When it's at rest, okay, so it's at rest. That's true. We can say the bowling ball is at rest to be in equilibrium. That's right. Move steadily in straight path. So it is moving steadily. Steadily means at constant speed, 2 meters per second. That is also true. Okay, as long as we don't change the speed, it's in equilibrium. That means both are true. So we have a scaffold, okay, and it is held by this string or rope, and a rope on this side, and there is a painter here, and the painter also has a bucket of paint. So the tension in this rope is 500 newtons. So this part is held by 500 Newton force, and this part is held by 700 Newton force. And the weight of the painter is 600 Newton, and the weight of the bucket is 100 Newton. And we need to find the weight of the scaffold. Okay, so what is the weight of the scaffold? So the basic idea here is the scaffold is in equilibrium. What kind of equilibrium? Is it dynamic? No, not dynamic, because it's not moving, right? That means it's static. And according to static equilibrium, the sum of force is 0. Okay. Now what kind of force we are talking about? We have the force in the upward direction and force in the downward direction. And we know that whenever the force is pointing in upward direction, we use positive sign. When the force is pointing in the downward direction, we use negative sign. That's the rule that we use in physics. Okay. So we want to find the weight of the scaffold, and let's assume that the weight of the scaffold is concentrated at the center. Okay, so that's the weight of the scaffold. Let's call this W. So what forces we have? 700 Newton. It is positive because it's pointing up. Okay, that's plus. We have 500 Newton force. That's also positive. It's pointing up. Another force is the force of the weight of the person. Weight of the person is 600 Newton. And is that right? Plus. Newton of the weight of the person is pointing down. So should I write plus here? No, I shouldn't write plus. This should be minus. Anything pointing down is negative. Likewise, the weight of the scaffold is also negative. It's pointing down. And then the weight of the bucket is also pointing down, so 100 Newton. Okay, so those are the forces we have. So 1, 2, 3, 4, 5 forces. And because it's in equilibrium, the sum of all these forces needs to be 0. Okay, so 700 plus 500, 1200. And then minus 600 minus 100 is minus 700. Okay, I'm adding this one and this one. So minus and minus, minus 100, minus 100, 700, plus 700 plus 500 plus 1200, and minus W is equal to 0. So 1200 minus 700, if you do that, you get 500 Newton. And then you can add W on both sides, okay, plus W on this side and plus W on this side. So this W and W will cancel because one is positive and one is negative. So we have 500 Newton on the left and we have W on right. That means the weight of the scaffold is 500 Newtons. So one of the forces we talked about is support force, and the next type of force is force of friction. Whenever an object is moving on some surface, so you have a surface and you move an object on that surface, then the surface will exert the force in the direction opposite to its motion. So if the object is moving to the right with some speed, then there would be a friction force in this opposite direction, okay, in this direction. So this is friction force. So friction force is always in the direction opposite to the direction of motion. And the reason there is friction force is because of the irregularities in the surface. So no matter how smooth the objects look, they always have some kind of irregularity in their surface. For example, let's consider this upper surface. You have on the upper surface you have these small tiny bumps, okay, and then on the bottom surface also you have these tiny bumps, and these bumps, they lock each other, okay. So the friction comes from those irregular surface at the microscopic level. No matter how smooth the surface are, there is always some irregularity in their surface. Newton's first law. What is Newton's first law? An object that is initially at rest, it stays at rest until some external force acts on it. Okay, as long as there is no force acting on the object, it will stay at rest. Likewise, if an object is moving, it will keep moving until an external force acts on it. So that's the Newton's first law of motion. Okay. Likewise, the example you see here is this object or this car tends to move in a straight path. This person and the car is moving in straight path. When you stop the car, the car comes to rest, but because of inertia, the person still tries to move forward. Okay, so the person lurches forward because of that. Newton's second law is about acceleration and force and mass. So it says that the acceleration you produce on an object is directly proportional to the force. Okay, so meaning twice the force, twice is the acceleration. You apply some force F on this brick. Okay, so let's say that force produces acceleration A. Now if you double the force, if you apply 2F force, that will produce 2A force, 2A acceleration. Okay, so doubling the force produces the double acceleration. That's the first part of Newton's second law. The second part is if you apply force F on mass m, you produce acceleration A. Okay, now you apply same force. Maybe I should compare these two. Okay, so because you are applying same force here, so let's consider this. Not this one. So this one and this one. Okay, this one and this one. So you are applying 2F force. Okay, on mass m, you produce 2A. Okay, so that's the acceleration produced when you apply force on some mass. Now when you double the mass but you keep the force same, what will happen to the acceleration? It reduces, right? So it will be 1/2 now. Sorry, 1/2 of that, which is A. So when you double the mass, that reduces the acceleration to 1/2. Okay, so acceleration is inversely proportional to mass. Your acceleration is directly proportional to force. Okay, when you combine these two, you get acceleration is equal to F over m. Okay, and that is the formula for Newton's second law, which is very important formula. So this is basically F is equal to ma, which we use very often in solving the problems. Okay, so this is also F is equal to ma. So what that means is larger the mass, smaller is the acceleration. Also, larger is the force, larger is the acceleration. So larger the force, larger the acceleration, larger the mass, smaller is the acceleration. You have 1000 kilogram car, and you apply 500 Newton force on that. So what would be the acceleration produced on that? We know acceleration is F over m. So force is, you are applying 500 Newton, and mass is 1000 kilogram. So 5, you can cancel 2 zeros on top, 2 zeros on the bottom. So 5 over 10. The unit for acceleration is meter per second squared. So 5 over 10 is 0.5 meters per second squared. So that's the Newton's second law. Newton's third law. Newton's third law is basically to every action there is equal and opposite reaction. So when you apply some force, there would be consequence of that force, consequence to that force. For example, when you push the road with your tires, the road will push the tire in the forward direction. Likewise, when the rocket propels the gas out, the gas will push or give the thrust to the rocket, moving it forward. When you are pulling the spring will also pull you with the reaction force. Okay. When you drop a ball on earth, the earth will pull the ball down. In turn, the ball will also pull the earth up. But we don't see that effect because it's negligible the pull of the ball on the earth is negligible, or the acceleration is negligible, I should say. Okay. We see the object accelerating down because it's small, but we don't see the earth accelerating up because it's very, very large. It's very negligible, so we don't see the acceleration of earth. Okay, that's Newton's third law. support force. So whenever we put something on a table, like here a book on the table doesn't collapse. Okay, the table doesn't break or collapse. The reason is there is this support force that is pushing this book upward. Okay, there is this weight of the book that is pulling this book downward, but also there is this support force which prevents the book from collapsing down or table from collapsing down. Okay, so this force is what we called support force. It is also called normal force.